In this video, we will talk about how to solve constrained optimization problems with Lagrange multipliers. So I want to look at the same example that we did in the last video, but solve it using a new technique. So the question, remember, was a cruise line sells two kinds of tickets to passengers, luxury and economy class. Economy passengers pay $2,000 for the cruise, while luxury passengers pay $3,500. The cost in hundreds of dollars of taking X economy passengers and Y luxury passengers is C of X comma Y equals this function of two variables. And everything up until this point was actually taken from an example in section 8.3 that we did. But there's one new thing that I'm adding to the example, which is this sentence. Also, now we're going to suppose that they sell 340 tickets total. So this is new to this section and the example as it's phrased now. And the question is asking us to find the combination of passengers that will maximize the profit. So we're going to talk about a second method for doing this. In the last video, we talked about method 1, which was substitution. Method 2 is called Lagrange multipliers. Lagrange multipliers. And one of the reasons that we want to have another method, as we commented on at the end of the last video, was substitution could be, particularly algebra intensive. It was tedious at times. So it'd be nice to have an alternate method. So with Lagrange multipliers, what we're going to be doing is we're going to try to find, to find candidates for local extrema of a function, multivariable function, which I'll write as f of x comma y comma, and maybe there's more variables, so I'll just put comma dot 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 if there's more, but subject to some constraint. So with a constraint, and I'm going to write the constraint as an equation, so there will be some function g of x comma y comma dot dot dot, depending on how many variables there are, and we're going to write the constraint so that the whole thing is equal to 0. So if it's not equal to 0 initially, we'll rearrange everything to have 0 on one side. Okay, so this is going to be the general outcome that we're trying to get with Lagrange multipliers. We're going to have some process that's going to find candidates for where the local mins and the local maxes happen. So there's two key steps to this. Step 1 involves constructing what's called the Lagrangian function. And the Lagrangian function I'm going to call L for Lagrange, L of x comma y comma dot dot dot, depending on how many variables there are. And it consists of the function f, my objective function, f of x comma y comma dot dot dot, and then minus this symbol. So I just wrote this symbol here, and then times my constraint, g of x comma y comma dot dot dot. And this symbol that I wrote in front of g is a Greek letter. It's the Greek letter lambda. Okay, and that's referred to as the Lagrange multiplier. It's multiplying this constraint function g. So in our example, let's set this up. So in our example, our objective function f was the profit. We wanted to maximize the profit. So this was our objective. And we set that up in the last video. So I'm not going to go through that one more time. Technically, we had set it up in an example back in section 8.3, so in the previous section. So recall that. The profit function was 20 plus x plus 35y minus 1 over 40 x squared minus 1/15 xy minus 1/10 y squared minus 800, where the initial part of this, 20x plus 35y, that was the revenue. Okay, so this whole thing, this is going to be our function f. Our function f, our objective is this profit function. So what is our constraint now? The constraint in this question, and we had written this down in the last video as well, the constraint is coming from the fact that they sell 340 total tickets. Okay, so if I write that down as an equation, so x is the number of economy tickets, y is the number of luxury tickets. If you add those together, that needs to be 340. That's our constraint equation. But if we look at the setup of Lagrange, it says that we need to get the constraint equation in this form, where it equals 0 on one side. So if we do that, if I move the 340 over, we'd get x plus y minus 340 equals 0. And this whole thing on the left, this is our constraint function, which we call g. In this case, g is a function of the variables x and y. So we are ready to write down this Lagrangian function. So I'll call it L, and my variables are x and y. So I write the function f, my objective, first. So the objective was this profit function. So it's 20x plus 35y minus 1/40 x squared minus 1/15 xy minus 1/10 y squared minus 800. And then I need minus lambda, that Greek letter, times the function g. So the function g is x plus y minus 340. X plus y minus 340. That's my constraint function. Okay, so all of this was f, and then I have minus lambda times, this was g. So the Lagrangian function is f minus lambda times g. Okay, so I can simplify this a little bit. Let's distribute that negative sign, and I'll get L of x comma y equals, this whole first part stays the same, 20x plus 35y minus 1/40 x squared minus 1/15 xy minus 1/10 y squared minus 800. Now I can distribute that negative sign and the lambda and get negative lambda x minus lambda y minus 340 lambda. So that's step one. Step one is set up that Lagrangian function. Construct this Lagrangian function. We are ready for step two now. Doing something with this function. So step two says the candidates for the local extrema, so for the local mins and the local maxes, occur at the critical points of that Lagrangian function, L of x comma y comma dot dot dot. I'm just writing comma dot 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 because we'll see examples later where there's more than just two variables here. Okay, so what we then do is find these critical points. Find these critical points. So what this is saying is the only places that the local mins and the local maxes could happen, the local mins and the local maxes of our objective function, which was profit in this example, could happen, are at the critical points of this Lagrangian function. So why is that? To answer that, we need some multivariable calculus. We need multivariable calculus, and that's beyond the scope of our class. So we're not going to answer why. We're just going to introduce this method and get practice and familiarize ourselves with how it works. So here is our Lagrangian function. Let's find the critical points. So we are going to need to take the partial derivatives, Lx and Ly, and set them equal to 0. Okay, so if I take the partial with respect to x, I'll get, from the first term, I'll get 20. The second term, I'll get 0, because there's no x's in it. It's treated as a constant. For the third term, I'll get minus 1 over 20x. For the minus 1 over 15xy, that partial derivative is going to be minus 1 over 15y. And then for the next term, it's 0. For the minus 800, it's also 0. For minus lambda x, that partial is going to be minus lambda. And then the remaining two terms are going to be 0, because neither one of them has an x in it. And notice that we're treating lambda as a constant when we do this. Okay, so that's the partial with respect to x. And we're going to set this equal to 0 to find critical points. Let's do the partial with respect to y. So for 20x, that's going to be 0, that derivative. For 35y, we'll get 35. For the minus 1/40th x squared, that becomes 0. There's no y's in it. For the minus 1 over 15xy, that partial is going to be minus 1 over 15x. For the minus 1 over 10y squared, that derivative is going to be minus 1 over 5y. And then the minus 800 and the minus lambda x don't have any y's in them, so their derivatives are going to be 0. For the minus lambda y, that partial is going to be minus lambda. And then for the 340 lambda, that's a constant, so that derivative is 0. All right, so we get this equals 0. Okay, so we took these partials, and looking at these two equations, actually let me number them. This is equation 1, this is equation 2. There is an x, a y, and a lambda. So there are 3 variables. So we need 3 equations, but we just have 2 right now. Well, actually, we do have a third equation. It was kind of given to us earlier on in the problem. And what we could use, the other equation, was the constraint. So we have to use the constraint to get this missing equation. This is going to be equation number 3. And what was that constraint? It was x plus y minus 340 equals 0. So at this point, we have a system of 3 equations with 3 variables. And I want to give you the opportunity to try to solve this first. This should be some review from algebra. So pause the video and try this for about 2 to 3 minutes. Let me just say 3 minutes to solve this system of equations. 4, 3, 2, 1. Pause that video. Pause it for 3 minutes and really try to solve the system. You're going to be doing a lot of these in Lagrange problems, solving systems of equations, and this can be the most challenging part of the Lagrange process, getting to the system of equations and trying to solve it. So it's going to be very useful to get practice with that now, even before you get to assignments. All right, so hopefully you've done that. Hopefully you've paused the video for about 3 minutes to try to solve this. Maybe it wasn't enough time to finish solving it, but hopefully you were able to make some good progress with it. So how could I get started with this? So I noticed that in the first 2 equations, they both have this minus lambda. So maybe we can move the lambda over to the other side. So I get lambda equals something in the first equation, and lambda equals something in the second equation. So maybe first, I will isolate lambda in equation 1 and 2. So in equation 1, we'll get 20 minus 1/20th x minus 1/15th y equals lambda. And from equation 2, we get 35 minus 1/15th x minus 1/5 y equals lambda. So because both of these equal lambda, we should be able to set them equal to each other. So that's my next step. Let's set these equal And I can do that since both equal lambda. And I should say that as we go through this, in these Lagrange multipliers questions, when you get your system of equations, there isn't one specific way to always solve every single system of equations. So I isolated the lambdas in these first two equations because it seemed like I was going to be able to do something nice after that, set two things equal. But that's not necessarily going to be my approach in every single problem. It just depends on what my equations look like, and then what I feel like a good approach to simplifying and solving those equations will be. Okay, but that's something that we'll get better at as we see more problems. And as that algebra starts to come back to us. Okay, so setting them equal, we get 20 minus 1/20th x minus 1/15th y equals 35 minus 1/15th x minus 1/5th y. So we can simplify if we get some common denominators and we rearrange this. So if I look at the x terms, the common denominator here would be 60. So if I take a negative 1 over 20x and I multiply the top and the bottom by 3, that is negative 3 over 60x. With negative 1 over 15x, to make the denominator 60, I got to multiply the top and the bottom by 4. And that'll give me negative 4 over 60x. So now if we look at the y terms, negative 1 over 15y and negative 1 over 5y, these ones are a little bit easier. The common denominator is going to be 15. So if I take the negative 1 over 5y term and I multiply the top and the bottom by 3, we get negative 3 over 15y. So let's rearrange these now. Let's move the x terms and the y terms, maybe both to the left-hand side. So if I add the 4 over 60x to the left, I'll get 1 over 60x. And if I add the 3 over 15y to the left, we'll get plus 2 over 15y. And then let me subtract the 20 over to the right-hand side. So 35 minus 20, that is 15. All right, so we have this equation now. So what else can we do? Remember, we also have the third equation in our system. So let's see if we can use that. And there's a few different ways that I could use that, but one thing I could do is I could substitute. So I could substitute x plus y equals 340, my constraint equation, into this, into what I have. All right, so if I do that, I'll get 1/60th x plus 2/15 times y. And if I isolate y, y is equal to 340 minus x. I could technically have isolated either variable. Both of them seem easy to do and plug in. I just decided to isolate y. And then this equals 15. All right, so I am down to one variable, so hopefully I'm going to be able to solve this. Okay, so looking at this equation, one thing that I notice is going to make it a little bit easier to solve is if I get rid of all the denominators. And I could do that if I were to multiply both sides by 60. So if I multiply this by 60 and the other side by 60, it's going to cancel out the denominators. Because when I distribute that 60 to the first term, I'll just get x. Because 60 cancels the 60 on the bottom. When I distribute it to the next term, 60 divided by 15 is going to give me 4. And then when you multiply that by the 2, you'll get 8. So we'll get plus 8 times 340 minus x equals 15 times 60 on the other side. If I multiply that out, that is 900. All right, so now I can distribute the 8. And if I do that, we will get x plus 2720 minus 8x equals 900. All right, so simplifying this, if I move the 900 over to the left, we'll get, let's see, 1820 equals, and if I move the x terms to the right, we'll get 7x. All right, so isolating the x, we get x equals 1820 over 7. And if I divide, this gives me 260. And if you remember the answer that we got in the last video, we were getting 260. So the answer we're getting from Lagrange is matching that, which is great. Okay, but the question didn't just want x. X was the number of economy passengers. It also wants y. So to get y, we can plug into our constraint here. Remember, our constraint was y equals 340 minus x. So if I plug in x, we get y equals 340 minus 260, which gives us 80 again. Same value we got for y in the last video using our other method. Okay, so we have x and we have y. So now we could write the x and the y as a point, as this is the critical point of our Lagrangian function. And remember, we were finding this because these are going to constitute the candidates where that max or min might happen. So I'm just going to write candidates. So the x is 260 at this point and the y is 80. Okay, so now we need to determine if there is a max or a min at the candidates. In this case, there's just one candidate, which is nice. Okay, so this is where we are going to make an assumption. If we go through this process of doing Lagrange and we just get one candidate, we are going to assume that it is what we want. So if our question was asking for a max, we're going to assume that this one candidate that we got is the max. If it was asking for a min, we're going to assume that this one candidate that we got is a min. If there's more than one candidate, so I'm writing if there's greater than one candidate, then what we will do is plug all the candidates into the objective. In this case, that was the profit function, but whatever function we were trying to maximize or minimize. And then we'll make an assumption. We're going to assume that the largest output is the absolute max, and the smallest output is the absolute min. So it's possible to show why this is the case in each example, but it's a little bit beyond the scope of our class to show why this is true. To show why this is true. This is something that I would talk about if this was a purely multivariable calculus course. But in our class, I'm going to focus more on being able to set up and perform these computations, so I'm not going to devote more time to this. Okay, so our final thing that we'd want to do here is just write our conclusion. The question wanted to know what combination of passengers gave us the max profit. So we know that the profit is maximized if the cruise sells 260 economy tickets and 80 luxury tickets, which is the same thing that we got using substitution. And if I zoom out and look back at this, if I zoom out and look back at some of the algebra that we had to do, so zooming it out a little bit more. So we had to set up this Lagrangian function back in step 1, and then after we had it set up, then we found the critical points in step 2. So we took the partials, we set them equal to 0. That just gave us 2 equations. So then we used our constraint to get a third equation. We needed that to have enough equations to match the number of variables that we had, which in this example was 3. But notice that the algebra that we had to do using Lagrange multipliers overall was simpler. It was less tedious than the algebra that we had to do with substitution. And that's a major positive to the method of Lagrange multipliers. Another benefit to Lagrange multipliers is, if I look at our constraint equation in this problem, it was x plus y equals 340. It was really easy to isolate one of the variables, so I could plug into the objective function. That's why substitution was doable. There are other scenarios where it's either challenging to isolate for one of the variables or just impossible. And if that's the case, I can't do it by substitution. And I would need Lagrange multipliers. So in terms of our goals for this section, we have now started talking about Lagrange multipliers and how we can use it to solve constrained max-min problems. But over the next few videos, we will continue to do more examples of Lagrange.